Hi, geology students. Welcome to our Igneous Rocks Lab lecture. We're going to review how igneous rocks form and the resulting textures and a bit about composition. And then I'm going to give you instructions for how to perform this week's lab. So hopefully you recall that there are two classes of igneous rock. First off, igneous rock forms from cooling of molten rock. If rock is molten, there's only one way it can go, and that is igneous. But there's two classes. There's intrusive igneous rock and extrusive igneous rock. And the difference between the two is where they cool. Intrusive rocks cool below the surface, and extrusive rocks cool above the surface. Or, if you will, this diagram that I stumbled across today by accident, but I'm going to use from now on, maybe that helps understand the difference between lava and magma. Anyway, the conditions below the ground are quite a bit hotter and pressurized than the conditions above the ground. And the result of this is that magma cools below the ground much, much, much more slowly than lava does above the ground. And this slow cooling has a direct influence on the rock's ultimate texture. In short, slow cooling forms large grains like what we see here. I mean, you actually can see those grains. If they were smaller, if they were the type of rock that cools quickly above the surface, you would not even be able to see any individual grains. And fast cooling forms small grains. So about 80% of identifying igneous rocks is really all about identifying the correct textures. So we're going to review these textures using some of the great photos from the people at geology.com. We'll start, not that, we've already seen that. Also, nice soil there. I feel like I could grow just about anything in that. So we'll start with the texture phanuritic. Phanuritic means large-grained, coarse-grained. Phanuritic is the type of texture that intrusive rocks have. Slow cooling leads to large grains. So when you are looking at an unknown igneous rock, and if you're going to decide to call it phanuritic, here's some things to think about. Are the grains large enough for me to identify? Can I see most of the grains? Also, do I have a lot of cleavage planes reflecting back at me as I tilt the specimen? As you tilt the specimen, those cleavage planes will continue to catch light and back at you. With the other textures, the cleavage planes are too small to catch light. They're there, but they're too small to catch light. So, intrusive rocks have a phanuritic texture. All rocks that cool above the ground, extrusive rocks, generally cool too quick for large minerals to form. So they all are small grained if they have grains at all. So let's look at these textures. So every texture from here, from the next slide on, is an extrusive texture. And we'll start with aphanitic, which means small grains. Now, aphanitic grains might be visible in your hand sample. Technically, they are a millimeter across or less. And so a sample like this basalt may have millimeter-sized crystals that you do not need magnification to see. But when compared to something like this, most definitely they are a lot smaller. So aphanitic rocks will have either very, very small visible crystals or crystals, grains, I should say, that are too small to identify, too small to even see without magnification. Another version of aphanitic is like this. And so you've got the occasional grain right there and right there and there. But for the most part, these grains are too small to see without magnification. This rock is somewhat similar in composition to this rock, but they look so much different because their textures are different. It's the same minerals here as here, and if you had high enough magnification, this rock would look a lot like that. But the fact is, these grains are too small for us to see without really, really high magnification. So aphanitic texture is going to be, number one, grains too small to see for the most part. But number two, even if the crystals are different minerals made of different colors. Those different colors are all going to blend into one. So aphanitic rocks are going to be fairly uniform in color, and they're going to be dull. They're not going to be reflective. Phanuritic rocks, again, have cleavage planes that grab and reflect the light. You're seeing this actually in the sample. I see a piece of feldspar that's giving us a really good reflection in the center of this granite. But aphanitic rocks will not give you that reflection because the cleavage planes are too small. Another version of aphanitic is called porphyritic, and it is an extrusive rock that nonetheless had a few early forming crystals below the ground, but the rest of the magma did not have a chance to solidify into rock yet. And so that was erupted as lava with crystals already in it. So the rest of that lava cooled quickly. So most of this rock, even though there are a few big crystals that we call phenocrysts, most of this rock is still composed of an aphanitic matrix. So this texture that's called porphyritic is really just a version, a subcategory, if you will, of aphanitic. It's still an extrusive rock, but at least one of your samples should have a good porphyritic texture to it. Lava that cools too quickly for grains to even form will have a glassy texture. Volcanic glass is, sure, we can call it a rock. I don't have a problem with calling it a rock, but technically it's not a rock because it's not composed of minerals. It's just composed of glass. The atoms in this glass froze in place too quickly to combine to form minerals. Instead, it's just mostly pure silica, silicon and oxygen atoms bonded together randomly without any sort of regimented crystalline structure. But glassy texture is fairly obvious to most of us. It clearly looks like glass, and also it should have a conchoidal fracture to it. And the other igneous texture that you're going to be looking at is vesicular, which simply means it's got a lot of holes in it. This is usually the result of a gassier than normal lava. As the lava is erupted, these gases come out of solution, and the space they're taking up in the lava gets preserved as the lava hardens around those gas bubbles. So as I said, 80% of this is simply identifying the proper texture. And once you have, then let's say you have 3 rocks of phanuritic texture or 3 rocks of aphanitic texture, the way that we separate those then is by their composition. And their composition, you may recall, is divided into 3 categories: mafic, intermediate, and felsic. Mafic rocks are composed of these minerals that you see here on the lower right. Felsic rocks are composed of these minerals on the lower left. These are light-colored minerals. And then intermediate is composed of a mix of mafic and felsic magmas, creating a different set of minerals. But these are mostly dark minerals, these are mostly light minerals, and these are mostly light and dark minerals. So mafic rocks will be identifiable either by, if they're phanuritic, by being able to identify these actual minerals, or if they're aphanitic, they're identifiable simply by looking at the color. Because even if they're microscopic, these dark minerals will still give the rock a dark color. Microscopic light-colored rocks will give the rock a light-colored color. So here is what I want you to do for this week's lab. It's a 2-parter, again, as usual. So let me put this down, and I want you, in your lab kit, I want you to get out samples 19 through 26. Samples 19 through 26 are the igneous rocks. And the first thing I'd like you to do is this particular document, and this is going to be posted right below this video, called Igneous Texture and Composition. And put your 8 samples where you think they should go. For now, Pay very little attention, if any attention. Do not pay any attention to the rock names in there. Instead, I want you to pay attention to the textures: phaneritic, aphanitic, and porphyritic, vesicular, and glassy. Put them in their right place based on their texture, and then if you've got 3 phaneritic and 3 aphanitic porphyritic, then put them in their right place based on these colors here. When you've got them in their right place, take a photo of that, and then check against the key, the sheet that comes in your lab kit, to see if you got them right. Is granite really the one that you had in this spot? Is basalt the one you had in this spot? Once you do get them rearranged in the right spot, then take another picture. That'll be your permanent picture. But take that picture. I may want you to post these pictures as part of your lab turning in, your final. In fact, let me just go ahead and say that. Part of your lab turn in, I want you to post the final picture of the rocks in the right place. But secondly, for your studying purposes, the other document is going to be called Igneous Rocks Data Sheet. And it's going to look like this. And so once you have those 8 rocks named correctly, and of course they have a key in them, so you're going to put each one in a slot there. And remember, if you have to type more than fits in there, it'll just simply go on to the next page. Don't worry about that. But I want you to tell its texture. Is it phaneritic, aphanitic, porphyritic, vesicular? What color do you note? What minerals do you see? If it is phaneritic, for example, I see a lot of pink potassium feldspar in here. You should know potassium feldspar pretty well after our minerals labs. If you don't see any minerals that you can observe, then what minerals should be in there? What minerals exist in there based on what you see here? And then finally, any other observations that you think will be helpful for you to help remember these rocks once I give them to you in a visual test, which will involve me having a little film of a sample and then telling you any sort of characteristics that may not be quite obvious on that. And then, of course, you will turn that in. So I want you to turn in 2 things this week, this completed chart and then a photo of your chart here with the rocks in the right place. Again, if you have any questions, do not hesitate to contact me. Bye.